Okay, so in this video we're going to discuss the last practice question, which is question 4. We're still drawing the shear and moment diagram. Now it's a simply supported beam. Okay, where there's a pin on the left and there's a roller on the right. So you're already familiar with this type of support. And the new thing that we have here is this distributed load. Okay, so distributed load is not something new to you, but it's new in this chapter. So we have not drawn the shear and moment diagrams when you have distributed load. Okay, but I assume that you know how to work this out based on the support reaction and all that. Okay, based on chapter 5 principles, you should know how to deal with distributed load. Okay, so we go straight to determining the support reaction. Right, so support, of course, here we have AY, AX, because it's a pin support and this is a roller, so there's CY. Okay, so AX, you can immediately put it as 0, and then we have two unknowns, AY and CY. So you can't use summation of force in y direction equals to 0. What we have to do instead is moment, calculate moment. So I'm going to calculate moment about point A so that we can find CY equals to 0. Okay, so to calculate moment about point A, we have two forces here. One is CY and one is the distributed load. So what's going to happen to the distributed load is it's going to be considered as a concentrated load. All right, so this will be its point of action at the center. So this is 2 meters. This is again another 2 meters, and this is of course 1 meter. Okay, at the center. So the whole load is across 2 meters, B to C. So the center of it, of course, it will be 1 meter from B. Okay, halfway. So the magnitude will be 1.5 kilonewton meters is given here. 1.5 times the entire length, which is 2. So that will give you 3 kilonewtons. No longer kilonewton per meter, yeah, because you've already multiplied with the length. So this load is considered as 3 kilonewton acting at this point. Okay, so back to calculating the moment about point A. So we have these two forces. Now the first one, I'm going to consider the 3 kilonewton. This will rotate, let's see, this way. Yeah, that's clockwise. So negative 3 kilonewtons times the distance is this point to point A. That will be 1 meter plus 2 meters. And then CY will cause a moment in this direction, so that's counterclockwise, plus CY, the distance will be the entire length of the beam, which is 4, equals to 0. And then CY equals, this is 9, am I right? So 9 divided by 4, that will be 2.25 kilonewtons. Okay, so that's CY. Now we can find AY. So the only two forces that we have, three actually, the three forces that we have are AY, distributed load, and CY. So treat the distributed load the same way as you would treat any vertical force here. So we take the concentrated load, which is 3 kilonewtons. Yeah. So AY is going up, the distributed load will be going downwards, and CY is upwards, so plus 2.25 equals to 0. Therefore, AY equals to 3 minus 2.25, that's 0.75 kilonewtons. Alright, so now all your support reactions are out of the way. We can cut section 1. Okay, so remember we always consider from the left side until before a change. So this is from point A. So the change is going to start at point B, where you start to have a load. So we're going to stop just before point B. That means here x is between 0 and 2. Yeah, so this is point A, somewhere there, and this is the shear force moment. Here we have AY, of course. AY, I'm just going to write the magnitude, 0.75. That's it. So summation of force in y direction equals 0. You will get V kilonewtons. Sum of moment about the sectioned end equals 0. So we have the moment itself, and then the force AY will cause a clockwise moment. So that's a negative. Yeah, this one will turn clockwise. So negative 0.75. The length is of course x. Okay, so moment is 0.75 x kilonewton meters. Let's just write the distance here, x. Okay, so for the next section, section 2, this is between 2 and all the way until the end, so that's 4. Okay, so what we have is, okay, this is a little bit unique. We are still going to treat the distributed load as distributed load first. Alright, so you can't use 3 kilonewtons because 3 kilonewtons is actually the load all the way from B to C, where in this case it's not from B to C. Okay, it's a range of values of x. Alright, so we have AY. This is point A and this is point B. Okay, this is point B, this is where the load starts. So I'm still going to draw the distributed load. Okay, so this is where we cut it. This is your shear force. This is your moment. And this is still 1.5 kilonewton per meter. Okay, I think those are all the forces. We don't include Cy because Cy is all the way at the end. Now, the summation of force, because we still want to determine shear force. So sum of Fy equals 0. What we have is 0.75 is going up, so positive, and then this distributed load. Okay, distributed load is going down, and of course it's similar to this, but it's not across 2 meters, so that's a bit tricky. Okay, so try to follow this. This is still 2 meters, and all the way here is x. It's not 4, it's x, and the remainder here will be x minus 2. Am I right? So this is 2, the whole length is x, this is x minus 2. Therefore, this distributed load, it will be distributed over x minus 2, depending on what x is. Okay, whereas at the top here we take it as 2 because it's 4 minus 2, and you get the entire length here. But now it's not 4. It's x minus 2, not 4 minus 2. Okay, so we need to keep it at that. Keep x as an unknown. So this will be the force here. I'm just going to sketch it at the center because you know what I mean. It will be 1.5 times x minus 2. That's the force. It's going downwards, so I'm going to multiply this. So 1.5 times x is 1.5x. 1.5 times negative 2 is minus 3. Okay, that's the whole portion of this force. And then we have our shear force, of course. So that's going downwards equals 0. 0.75 minus 1.5x plus 3 minus v equals 0. So rearrange v equals 2. 0.75 plus 3, that's 3.75 minus 1.5x. You can also write it as negative 1.5x plus 3.75. It's the same thing. Okay, so to find moment, same way, moment about the sectioned end equals to 0. So we have three things here. Yeah, I'm going to use a different color so that you can see more clearly. So here we have this force. Remember, this is the moment that this is the point that we are going to consider. So y will be going this way. And then we have this moment, of course, to include. And then we have this force. Okay, this is based on the distributed load and the length that it's acting on. So this is the force. Then to calculate the moment, we need to know the distance. So of course, it will be between this point and this point. So if the whole point from B to the end is x minus 2, halfway will be x minus 2 divided by 2. That will be the distance here. Alright, this is halfway. So x minus 2 over 2. Okay, so let's put all of that down. So don't forget the moment that we have at that end. This will be clockwise, so negative 0.75. The distance is x. And this will be counterclockwise. Alright, oops. Okay, this force will be going counterclockwise. So plus the force is 1.5x. I'm gonna multiply it minus 3. Okay, same as what we had here. Times the distance, and the distance is x minus 2 divided by 2. That's it, equals to 0. So solve this. Alright, as in get the equation for m. So I'm going to expand it first. Plus 1.5 times x divided by 2, that would be 0.75. Just going to put this all in a bracket first. 1.5 times x divided by 2, 0.75 x squared. 1.5 times negative 2 divided by 2. Okay, so you can also, of course, work it out however way you're comfortable. Okay, where was I? So 1.5 times minus 2 divided by 2 just now, right? That would be minus 1.5 x. Okay, and then minus 3 times x divided by 2, that will be minus 1.5 x. And minus 3 times minus 2 is 6 divided by 2 will be 3, so plus 3 equals to 0. Now you can rearrange this and get m. Of course, I hope you are writing this down on a piece of paper so that you can check. Okay, you don't have to follow how I'm expanding this. Moment equals to, we write the x squared term first, 0.75 x square this one, right? Move to the other side, and for the x terms we have negative 0.75 minus 1.5, that is minus 2.25 already, minus another 1.5 will be minus 3.75. Move to the other side will be plus 3.75 x, and then 3 is the only constant we have there, so minus 3. That's your final equation. Okay, so now we take the equations that we have. Let's see. There's only two sections. So this is the equation for shear force, equation 1. And then this is shear force, equation 2. And then this is moment, equation 1. And of course this is moment, equation 2. Okay, so I'm going to take all this to the next slide to draw the two diagrams. Okay, so let's draw the shear diagram first. V and X. Okay, this is point A. So we start with V equals to 0.75. This is between 0 and 2, right? At point B is 2. So between 0 and 2 is a straight line. Please forgive my not so straight line there. This is 0.75. So there. Okay. Next, here is a linear equation, one unknown. So just try put 2 inside here because this is between 2 and 4. If you try putting 2 times 1.5 is 3. So 3.75 minus 3, you'll get 0.75. So it checks out. You start here, and then at x equals to 4, so that will be 4 times 1.5 is 6. So 3.75 minus 6 will be minus 2.25. So that's down here. Let's just say it's down here. Minus 2.25. So that's somewhere around there. Okay, for this is 2, this is 4. So it's just a straight line. Alright. So how do you shade this? What you can do is just shade the region. Whoops. Shade the region. Alright, here. And this as well. Okay, because it starts from here, it goes downwards. Okay, that is a very lopsided shear diagram. For the moment diagram, okay, that's a bit better, I think. So this is moment. This is x in meters. Okay. Okay, so I'm just, because I have space here, so I'm covering both the positive and negative y region. You don't have to. Okay, so this is in the case where you don't know how the graph is going to look. So now let's figure it out. For between 0 to 2, it's a linear equation here. So it will intercept at 0. Okay, when x equals to 0, m equals to 0. When x equals to 2, m equals to 0.75 times 2, which is 1.5. So let's say this is 2. This is 1.5. Somewhere there. this will be about here, right? That is fine as long as you see it's a straight line. The label marks 1.5. And for section 2, this is a little bit more complicated, and the reason is it's a quadratic equation. So I think you're quite familiar with quadratic equation. I can give you a link later for you to understand it better. So basically what you have in a quadratic equation is ax plus bx plus c. Okay, a is a magnitude of how open or closed the curve is. Okay, so you know quadratic equation results in a symmetrical curve, something like that. Okay, not very symmetrical because of my sketch, but I'm sure you know how a quadratic equation, how the graph should look like for a quadratic equation. So this negative sign in front of the x squared, this is our a. So this means that the graph is looking like this. Okay, this is what we are expecting. The graph will be looking like this, downwards like that. Alright, and of course I think you've learned somewhere in mathematics that the x-intercepts is given by the root of the function. We don't have to find that. You can, but we don't have to. Okay, what you can do instead is just find the peak, okay, the vertex of the curve, because we know it looks like that. We know it looks like this. So how is it going to be on our graph? Okay, how is it going to fit? So I just want to find the vertex just to see. So to find vertex, the equation is, let's see, vertex equals to minus, hang on, minus b over 2a. So in this case, minus b is minus 3.75 over 2a is 2 times minus 0.75. So this will give you 5 divided by negative 1.5. Okay, so this means that the vertex is, just divide the number, equals to 2.5. Okay, so we know it looks like this. So this peak is at 2.5. That means it's 2.5. Let's just say it's somewhere there. This is very important to label, yeah? So that's the peak. We still don't know whether it's here or here or here or here. Right? But at least you know that this is the maximum part of the curve. So now you can start to put in the numbers. Okay, so you can try to put when x equals to 2, what are you going to get? X equals to 4, what are you going to get? And if you want to be more sure, you can put x equals to 3 also. Okay, so when x equals to 2, we won't be using the space here, so I'm just going to write here. When x equals to 2, moment equals to, so that will be 1.5. Okay, so this is where it meets. Remember the peak is at 2.5, and when x equals to 4, moment equals to, again, please calculate this, 0. Okay, as expected, it will be 0 at the end of the beam. So here we have this. Okay, so this is 0 at the end. So keeping in mind that you want to produce this quadratic curve. So let's just say the center is somewhere there. So it's going to go up and down. This is the basic shape. This is the peak. This is where the points that we really know. If you want to be sure, then I suppose there's no harm in calculating this value so that you can find a nice point here. You can calculate this value, you can calculate this value. Okay, there's no harm in doing that. Okay, so basically that's it. You have covered all the types of forces and moments and beams that you need to know in order to draw the shear and moment diagram. I know that this is a pretty complicated type of question. Okay, so maybe in our revision later on, before test 2, maybe we can do a few more questions. Alright, so that's it for now, and the next time we'll meet is going to be covering chapter 8.